All right. Hello, everybody. Um, let's go ahead and do 11.2, number 14a and b. There's a beautiful question somebody asked about, and really like it. So let's do part A first. So part A says find a graph G where both G and G complement are connected. And I have a favorite example of this, and my favorite example of this is sometimes denoted by C5. It's a cycle on 5 vertices. Okay, if you take that graph and get the complement, so maybe what I'll do is I'll draw that with red. You get that. Which is certainly connected. Yeah, and that's the only, that's all I needed, that both G and G complement be connected. Great. That's part A. Part B. If G is a graph on n vertices, for n greater than equal to 2, and G is not connected, prove then that G complement must be connected. All right, this is nice. So we start with if G is a graph on n vertices. Okay, so let G be a graph on n vertices, n greater than or equal to 2. And now we need to prove that if G is not connected, then G bar is connected. So now we assume G is not connected. All right, so what does it mean to be not connected? It means there's at least 2 vertices where there is no path from one to the other. Another way to look at it is we've got components. Remember what a component is? A component is a maximally connected subgraph. So we've got at least 2 components here. So let's call it A be the vertices in a component that is a maximally connected subgraph of G. So A is the set of vertices in one component of G, so everything in A is connected. And let B be the vertices of G minus A. So let take B to be everything else. So what we have here is I split G into 2 sections. I've got A and I got B. Everything B is just everything else. A is connected. Okay. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Since G is disconnected and n is greater than or equal to 2, B is not empty. That's something important to notice. A is not empty and B is not empty. Now there might be 17 components here. I don't know how many components there are, but I know I've got one on the left, A, and then B is just everything else. This is part of the trick. So now what I want to show is that G bar must be connected. So how do I show G bar is connected? How do I show complement is connected? I need to show that for any 2 vertices I pick, I can find a path from one to the other. So let's do that. Let U and V be any 2 vertices of G bar. I'll just emphasize that. I'm going to find a path from U to V in G bar. Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example.
Well, the vertices in G bar are the same as the vertices in G. And so those vertices are split into groups A and B as well. If U and V are both or are in different groups, if U is in A and V is in B, or U is in B and V is in A, then the edge UV is not in the edges of G, and thus UV is in the edges of G bar, and thus U and V are connected by a path, an easy path. Just they're directly connected. They are adjacent. So if the U and the V are in two different sets, so if one of the U's over here, one of the vertices over there, and one of the vertices is over there, then because of the way I define this graph, everything in A is a component. Nothing is more connected to anything in there in G. And so in G bar, these cannot be connected in G, and therefore they must be connected in G bar. And we're done. On the other hand, if U and V are both in A, then let B be any element of B. And I can do that because B is not empty. Then the path U to B to V is in G bar, right? If I have, so let's draw that picture. Here's my set A, here's my set B. If U and V are both over here, then pick anything at all over here, and I know I can do that because I mentioned earlier how B is not empty. Then I have an edge V to V in G bar, and I have an U to B, and I have an edge from V to B. And so therefore I have a path from U to V. Well, and then there's one more possibility, and it's the exact same thing, is if they're both on the other side, if they're both in B. Now, the only difference is if they were both in A, then in the graph G, I knew they were connected. So I know they're not directly connected there. If they're both in B, they might actually be both connected in B already, but I don't know that. And so what we do now is, again, the same idea. So if U and V were both in B, then let little a be anything in A, and we have the path U to A to V is in G bar. Thus, U and V are always connected by a path in G bar, and thus G bar is connected. Done. Very, very nice little proof. Looking at components and looking at where those where the vertices could end up. You have to pick. And yeah, hopefully that helps you. Have a good one. Talk to you soon.
Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.